Okay, so we'll be starting in just under a minute. We've got a hard stop after an hour, so I'll waste very little time on courtesies. But first of all, thank you, obviously, Michael, for making yourself available and for,
Thanks for hosting.
yeah, such a pleasure, and obviously generously donating your time to American Humane. Is there anything you want to say about that charity that caused you to want to choose that as the one we are raising money for?
Just that I think they do really work with some beings that have a hard time advocating for themselves, obviously. So it's our responsibility to do it. And yeah, thank you all for contributing.
Brilliant. Great. And yeah, so obviously it's an experimental format, slightly less experimental since we've done it once before, and it seemed to work out pretty well. Um, just apologies in advance. I have quite a intense cold today. So if my brain is a bit hazy or hazier than normal, um, please excuse me. Generally, so just to explain, in case it's not obvious, the people have donated money for the privilege of asking a question, having a short dialogue with Michael. Um, he won't necessarily have a whole lot to say on all of them. It's if it's well outside of his area of expertise, and I'll just give a little kind of time notification after 5 minutes and try and limit every question to 10 minutes so that we get through at least six. And just upfront, huge thanks to everyone that contributed. Lots of people donated without asking questions. There's lots of people here who just are happy to hear the Q&A and support the charity. I will try and copy and paste the questions into the chat as we go, although this first one is longer than the Zoom chat allows. So also some people have asked if they can read their own question. And if that's the case, then I will just invite you to do so. If after a few seconds you don't unmute and ask your question, then I'll just go ahead and ask it myself. So, okay, it seems like it's not letting me paste it because it's too long. Okay, so here we go. So there's on the event page, there's some references and some links to previous conversations recorded on YouTube regarding this question. It relates to this person's project on dual aspect monism. There's a link to a paper that he wrote. His name is Stephen Jarosek. So thank you, Stephen, for this question and your generous donation. Association, conditioning, associative learning is an important concept in semiotic theory, CSPS. Birch, Ginsberg, and Jablonka introduce unlimited associative learning, UAL, as a benchmark for establishing cognition in living agents all the way down to the cellular level. What do you think of association, or UAL, as a fundamental principle in top-down causation, which begins with multicellular organisms such as us, and which extends not only to the cellular level, but also to the subatomic domain to include the subatomic agents depicted in Feynman diagrams? Do you think I need to read more of the background, Michael, for your answer to make sense? Or
No, well, yeah, I mean, I've read it. I think
okay.
what's not super clear to me is and I don't know if he's here on the call, and if he is, maybe he can clarify. What wasn't super clear to me on that is whether there's a whether there's a concrete question or just kind of to give my thoughts. So I suppose I'll just give some thoughts. I do think that learning in particular and other aspects of cognitive functionality extend well below the cell level as well. So I think it's quite reasonable to see those things in very basal forms. I mean, we see them in groups of chemical networks, for example, that not even a cell or anything like that. I mean, I think they show up very early on, or like very kind of on the low scale of organization. So I think that's perfectly reasonable. I think that Ginsberg and Jablonka's UAL is excellent, but I would say that it's actually I think it's actually more general than that. So it's not just associative learning, but there are other forms of learning that I think we could use as a basic principle that underlies a lot of what we tend to think of as a kind of mechanical events down below, sort of below life. So yeah, I don't know if that's what he was going for. Yeah, I think using these kinds of concepts from behavioral and cognitive science to analyze things that previously were thought to be the province of, let's say, physics and chemistry, I think it's a good project. I'm not sure unlimited associative learning is available all the way to the bottom, maybe, but some of these things I think certainly are.
Yeah, and I think Steve is on the call. You mentioned by email that your camera's broken, so you might not be able to respond talking if you don't want to, but you can put something in the chat if you have a follow-up, and I can come back to that. Just so everyone knows, he also wrote a paper, and you gave some notes on the margins of that paper as well, Michael, didn't you? Okay, so unless Steve, you want to follow up with something in the chat, we can circle back to you. And I'm just because we've got like a hard stop on the hour, I'm just going to keep things moving. Alex, Warren, you said you would be happy to read your question yourself.
Okay, so I come to the Q&A previously with Bernardo Kastrop, and I was asking kind of some generic questions and got the response that science works best with repeatable types of things. And so, yeah, I'm still kind of curious about these, like how things apply. For instance, the organizational design questions of like teams, et cetera, of people. um, there's this idea of like naturalizing sense making. So using principles from cognitive science to inform like hypothesis about what might work better or worse with groups. And and then I've been kind of wondering about the space of competencies. Um, and then also, I was listening to some of the talks y'all have with Mark Solms and kind of reading into his point of view of things in active inference, and affect. And I guess maybe a way to make my question more concrete is I was like, oh, well, what don't I know about is like the uh like there's all the neurotransmitters and as far as like how does the brain develop and the electrophysiology of that. I realize I'm not really familiar with what people say about that sort of thing, but I wondered if that was perhaps a bridge from this like lower cellular level to like a whole brain having instinctual tendencies. And yeah, so I'll leave it at that. That's kind of like where my thinking is going.
Okay, well, let's see. Well, first of all, so neurotransmitters have existed long before brains and neurons. So the nervous system co-opted certain molecules that exist in plants in embryos before the formation of neurons, and all sorts of biologicals, things like serotonin and so on are extremely ancient molecules, and they were co-opted for roles in the nervous system. At some point when nerve and muscle came on the scene. I think one way to think about the construction of the brain and of behavior in general is that it evolved that system for solving problems in three-dimensional space, meaning moving you or moving the body or the animal around in three-dimensional space, evolved from much more ancient principles that were needed to move the individual around in other spaces. For example, the first thing as an embryo you have to do is navigate anatomical space. So you start off as let's say an egg, a single cell, and you have to get to some morphology, whether it's a giraffe or a human or a snake or whatever it's going to be. And navigating that space and getting to where you need to be is a very kind of interesting and complex problem solving task. And cells were doing that and navigating that space using memory and error minimization and decision making and things like that long before nerve and muscle came on the scene. So what evolution I think did is pivot some of those tricks and in fact the mechanisms used to navigate that space into a new space when nerve and muscle came on the scene. It also sped up the process because it was a sort of arms race to see who can catch whom once things started running around and crawling around and so on. But I think you can tell the story of evolution as a progressive set of pivots, possibly first in metabolic space, right? So your earliest concerns were about metabolism and energy, and then physiological state space when you're trying to keep track of and manage various physiological states. And at that point, you get things like ion channels already, and this is what, bacteria already have ion channels, and bacterial biofilms already use electrical communication to integrate information across space and time. Already, bacterial mats do this, and so this again was figured out by evolution very early on in the process. And then after that, true multicellularity kicks in, and now you can navigate. Well, first the transcriptional space, meaning gene expression space, and then multicellularity kicks in, and you can navigate now anatomical space, which didn't exist when you're single cells. There isn't any large scale anatomical space to navigate, but as a multicellular organism, you can. And then of course 3D space once nerve and muscle showed up, and then linguistic space with humans, and who knows what other kind of spaces are out there. So yeah, I think some of the same mechanisms, meaning electrical networks and some other things, chemical networks and so on, are ancient, and some of the same algorithms, the ways in which to process information, ways in which to make decisions, to coarse grain your reality, to have goal-directed error minimization, things like that, are way older than brains. And so yeah, it's the story of evolution. It's the story of life projecting its problem-solving skills into new problem spaces as the complexity goes up.
Anything you want to follow up on that, Alex?
Yeah, that makes sense. I guess so I've wondered, is it reasonable to try to find ways to say parallels, or I feel like I could study math more, but I imagine that there's there's the spaces of linear algebra. Does it make sense to talk about some sort of topologies of competencies, or I don't know, there's like the ways that that's talked about in computer science. I'm not sure if there's a similar way to say like a cell is navigating transcriptional space. I'm not sure, how similar is the spaces I navigate, I don't know, in my own conceptual life. And so I'm wondering, is there like regularities or constraints, or like I guess the alternative is like complexity is always sort of idiosyncratic, in that it's always sort of needs to be addressed on its own terms, or I don't know. That's kind of.
I mean, no, well, I think, and of course that could be because we're missing a lot of the idiosyncratic details, which is always possible. But I think there are similar principles across all kinds of weird spaces. So, for example, in a recent paper, we studied the journey of a computer sorting algorithm. Right, these are algorithms that sort strings of jumbled up numbers into a progressive sequence, right, a monotonic sequence. And you can visualize the process of a sorting algorithm doing that to an array of numbers as a walk through sorting space, right? Where there's a single point where they're all going, which is when everything is sorted, and then there's all these other points when things are not sorted. And so once you visualize it that way, you can do some of the same things that we do in animal behavior, for example, when we ask questions like, so how much ingenuity does this thing have to reach its goal, right? You can visualize the path that it wants to take in that space, and you can say, okay, so if we put a barrier in, what does the system do when confronted by a barrier? We have all kinds of different systems. So, for example, two magnets. If you put a piece of wood between two magnets, they're not smart enough to go around the wood and meet each other, because that would require them to go temporarily away from their goal, and they're not smart enough to do that. All they do is go downhill in their gradient. But actually, the sorting algorithms, which are extremely simple algorithms, and no one knew until we looked, no one knew that that they had this property. They actually are smart enough to do that. And so if you put barriers in that space, they can do delayed gratification. They can walk away from their goal, get further from their goal in order to recoup gains later and go around the barrier and get to where they need to be. This is completely an emergent competency. It is not visibly apparent from the algorithm itself. The algorithm is like 6 lines of code. It doesn't do any of that. So that tells us a few things, but one of the things that relevant to your question is that I think taking these basic concepts we have for what does it take to navigate a space intelligently, in other words, find new solutions to problems, and do things like delayed gratification and memory and so on. It's pretty fruitful to look for those things in unconventional places. So and we're finding them all over the place in our work. So I think there are major invariants across all of these systems.
Brilliant. Thank you so much, Alex.
Thank you.
Great. Aradhana, apologies if I'm mispronouncing that. I've also your
Yes, it's Aradhana.
Aradhana, great. Yeah, you wanted to read your own question, right? Yes, go ahead.
Yes, I just want to say it's such an honor to talk to Mr. Michael Levin, because whenever I am not working or doing my daily mundane activity, consider you or Bernardo Castro, this feels like.
Sorry, I cannot hear very well that part. Say that again.
No, I'm saying whenever I'm not working or doing my daily mundane activities, it's either you or Chris Fields, Bernardo Castro, and Carl Friston, Christoph Koch. That's all I listen to. It's like it's like meeting, I don't know, the lead guitarist or lead singer of my favorite band or something. So thank you, Adventures in Awareness and Dandelion Events, for making this possible. Please. So just
Your audio sometimes goes a bit quiet, so just
Yeah.
FYI.
yeah, I'll come closer. Is this fine?
This is
Yeah.
better.
Am I audible? Yeah.
And also, Michael, the questions in the chat, if
Yes.
it's hard to hear.
So I just want to a little better. So my question is more about the origin of life. So is it useful to wonder what came first? The most minimalistic system that's capable of observation, which would mean some minimal interaction or information exchange across a boundary, or the most basic form of a lifelike embodiment, or self-replication. So see, is it possible that as a result of millions of years of observation by a minimal system, a need for self-replication arose so as to sustain this observation? Or maybe even a random occurrence of self-replication of the minimal observer proved conducive to observation, hence it started to occur more and more. So I would let Michael answer this, and I can then see why this idea even came to my mind. So if you want to answer this, I could elaborate further.
And maybe whilst you could potentially also write in the chat your follow-on thought, because it's a little hard to hear you. So just a FYI, but yeah, carry on, Michael.
Right. But was my question audible? And this is the question that I wrote in the initial.
Yep, I got it. Yeah,
Yes.
I got it. Yeah, really interesting and difficult question. I don't know. My suspicion is that if we are committed to really being able to look at very minimal, really minimal observers, like really minimal ones, I suspect that predates self-replication. I think self-replication, with some degree of error, is a fantastic mechanism for expanding the proto-cognitive competencies.
Correct.
But I suspect it came after the fact. I think that the most minimal version of this predates all that. And I think overall, so there's different theories about what is it that reproduces differentially. So some people say it's genes, some people say it's information, right? There's a few things. I suspect what it is perspectives. I think that what we actually have in the biosphere and outside the biosphere are different ways to observe the world and to coarse grain the world and to make meaning of the world. Again, even in very potentially in very minimal sense. And I think that's what all the competition is about. It's a competition and a differential proliferation of observers. And so the proliferation, I think, comes after the ability to do this. I think is very fundamental. I think it's baked in at the very bottom of the universe, as far as I know. I mean, who knows, right? This is very difficult.
Right. So actually, the idea of I even thought about this because you describe intelligence as goal-oriented behavior. Right? So even the concept of a goal, to conceptualize what a goal is, it needs to arise from like a pre-concept stage, like what a goal is. So I don't know if this is a good example. Like I'll try to give you an example. For instance, the goal of food, right? So like one fine day, this minimal observer, a speck of something that gets closer to this observer, instead of killing it or stopping it or ending it, it sustains it. So I'm not saying that was the birth of food, but if something like that occurs over a sufficient period of time and enough number of times, such a concept can be born. And maybe like your cognition and intelligence and even emotions when humans arise, so they are just like version upgrades of the most minimal observation. Like millionth version of observation is intelligence. So obviously from it was not a leap from the protocognition to the intelligence, and there were many stages, pre-intelligence stages, but every stage was useful, and it happened enough number of times to finally be this version upgrade that has intelligence and cognition. But the initial thing is the minimal observation system that exchanges information across a boundary. So this is how I thought of it.
Yeah. I mean, I think you could definitely tell a useful story like that, and I mean that's something that I think Chris Fields and Carl Friston have both done in terms of active inference in very minimal quantum systems. So I think it's already there. I'm not going to try to recapitulate their story, but I will just say that if we're really willing to accept very minimal versions of these things, then I think it's actually long before you get to food or anything else. And in the physical world, I think the very minimum in our universe, the very minimal version of goal directedness is least action principles. And here's what here's what I mean by that. My definition of intelligence is basically William James's definition, which is the ability to reach the same goal by different means. And that doesn't mean you have a metacognition where you know what your goal is. It's very much a kind of an observer's a relative view, meaning that we as observers look at a system and we ask ourselves, okay, can I use the formalism of having a goal, having ingenuity to pursue that goal? Can I use those things profitably to describe the system, right? It's kind of like Dennett's intentional stance. It's that sort of thing. So I think if you do that, you will find out that in our world, there is no zero here because even particles will follow least action laws. For example, a photon of light will choose a least action path out of many possible paths. Magnets going down a gradient will do it. And the reason that I think it's useful to call that goal directed, because some people will say, well, why are you calling that goal directed? It's just mechanical, it's dumb rolling down a gradient. Why is that goal directedness? Well, I'll tell you why I think that. I think fundamentally what we're looking at is a spectrum of what I call persuadability, which is different degrees of autonomy in a system. As an engineer, I look at a system and I ask myself, what can I count on this thing to do autonomously without me being there, right? If it's a human, I can count on quite a lot. If it's a rat, I can count on something. If it's a cell, I can count on it doing some things on its own. But if it's a thermostat, I can count on it doing a very specific thing on its own, right? I don't have to be there to keep a certain temperature. The thermostat will do it. So the degree of autonomy of a system, I'm not going to expect a thermostat to be able to change, pick up new goals, be creative, but it's not zero. It can keep the two very specific goals, right? So when you as an engineer build, let's say a roller coaster, so you spend a bunch of effort making sure the thing can get up the hill, you don't need to do anything to get it, to have it go down the hill. That's autonomous. It does that on its own. So it's not super clever, but it's not zero, right? The thing has some autonomy. You can count on, in fact, you can engineer things. As an engineer, you can 100% count on the fact that that thing will do that on its own. You don't have to worry about getting it down the hill. So just the ability to follow a gradient, to go down the gradient, it's not high on the intelligence scale. It's really low, but it's not zero. It's already a degree of autonomy. And I think that's the basis of all of this, being able to follow these kind of least action principles are the smallest kinds of goals that exist, and they go all the way to the bottom in our universe anyway.
Okay. Thank you. And again, it was an honor talking to
Thank you so
you.
much. You're very kind.
Thank you.
Thank you for that question. Thanks.
Thank you so much, everyone, for your great questions. I forgot to mention this event has raised over £630, which is about almost $800 for American Humane. So thank you.
Thank you all so much. Yeah, amazing.
Thank you again, everyone. This next question Oh, they requested that I read it. So the question is your work changing only the current biological paradigm or also physicalism? What are your thoughts about panpsychism, idealism, and process philosophy?
Okay. Well, so yeah, so here's the thing with physicalism. Well, let's start with that. I think it's pretty clear to me anyway that important things that serve as causal forces, that are important ingredients in explaining why certain things happen, and in particular in helping you invent new things and control certain events and so on, are not coming from the physical world. And what I mean by that, I don't mean anything too exotic. I mean, well, maybe it's exotic. It's the same thing that Platonist mathematicians. So I'll just give you a very simple example. Imagine in this world where the highest fitness is a triangle of a particular kind. Yeah, so you have a population of different shapes, and the highest fitness is a very particular kind of triangle. So evolution cranks through a bunch of generations, and you find the first angle, and that's great. And then it cranks through a bunch of other generations, and you find the second angle, great. Well, now something very magical happens. You don't need to spend time looking for that third angle. Okay, for some reason, you know what the third angle is. You got it. Evolution just saved 1/3 of its effort in searching this thing. Now, so this is not philosophy. This is very practical. You've just saved a bunch of time in evolution. Where did that come from? I mean, as biologists, we love two things. We love environment and we love heredity. So was that part of your heredity, the fact that in the flat space, triangles add up to 180 degrees? Well, not really. Was it part of the environment? Well, not the physical environment. It came from somewhere else. It came from the same place where the distribution of prime numbers comes from, and the truths of number theory, and the fact that NAND gates in computer science are special, and just all these. There's an incredible richness of these patterns. For want of a better word, there are these patterns, and I think evolution exploits them extremely well. I think that's what evolution's actually doing, is that by evolving physical bodies, what you're really doing is evolving pointers into this Platonic space of patterns. I think that evolution exploits these free gifts. Here's another example. If evolution discovers a voltage gated ion channel, right? That's a voltage gated current conductance. That's basically a transistor. So you've discovered this protein. Well, automatically you've made a transistor, which means if you have a couple of them, you can make logic gates, which gives you a truth table with some interesting properties. You can do computation. You didn't have to evolve the truth table. You didn't have to evolve any of these properties. If you're a sunflower and you're doing the Fibonacci series, that has some amazing properties. All of those are kind of free gifts as far as the physical world is concerned. But what evolution has to do is to find a way to make a physical object that enables that stuff to and this is a word that Whitehead, I think, used to ingress into the physical world. So all of these truths of mathematics that apparently don't depend on the physical constants of our universe, right? So at the Big Bang, if we reshuffled all the physical constants, all the stuff about the physical world would be different. But these mathematical truths would still be there. These forms would still be there, right? These patterns would still be there. So from that perspective, my view is distinctly non-physical, because I think that these things are important and causal. And then here's the important step. Of course, all biologists know about this stuff, but one thing that people do when they encounter these patterns or interesting properties of networks, for example, such as Stu Kaufman discovered, and all these things, what people will say is, well, it's a fact that holds. These are just facts that, why do all networks have this interesting property? Well, it's just a fact that holds. That's just it. So the problem is, if you just call these things facts that hold, it's really, to me, that's really a very Mysterian view. What you're saying is there's a random bag of facts that hold out there somewhere, and we do things, and then we get surprised. Hey, look at that, it's and they'll say it's emergent, right? So this is emergent. Well, that's great. It's emergent, and we got surprised, and it's cool, and we write a paper about it. Now, how about finding the next emergent thing? well, I don't know, we'll just have to make stuff and hope something else emerges. So I don't like it. I think that I think it's very much a kind of a pessimistic or a defeatist attitude. I think the whole point of doing science is the assumption. It's very much an assumption that there is order behind all of it, and it's not a random grab bag of stuff. So I would prefer to think as at least as many, not all, but many mathematicians think, that this is not a random set of stuff that just magically emerges, but rather the space of these patterns has order to it. It's an actual structured space. And that our research agenda here is to actively explore that space. That by making, now how do you explore that space? Well, we make these pointers. Evolution isn't the only process that gives rise to these pointers. We make them too. When we make xenobots, these little autonomous beings that are made of frog skin cells, what we are doing is exploring the space around the normal frog embryo has shown us one point. There's one point in that space. And many of us tended to think that, well, that's all the genome can do, is it's responsible for that particular shape and that particular behavior. But actually, it turns out that no, that hardware can do a lot of other things. And you can use that as a vehicle to explore what's next to that. And then you can sort of branch out from that. I mean, if you look at the mathematicians, they literally have a map. Like there's a map of mathematics, and they can say, okay, so here's topology, and then here's I don't know, number theory, whatever. So they already believe that there is a space, and it's a structured, ordered space that we can characterize by effort and by rational thought, and that what they're doing is discovery, not invention. That they're discovering these things, they're not inventing them. And I think that's very much true here. So in that sense, I break with physicalism, because I don't think it's sufficient to understand the hardware or aka the pointers. I think you have to understand what the pointers are pointing to. And as far as I can tell, and I'm open to being proven wrong if it goes that way. But what I see is that the forms that it's pointing to are not determined by physical facts, which takes us outside of physicalism, but not into the area of Mysterianism, because that's the thing, right? A lot of people are tied to physicalism because they believe that if you abandon physicalism, then anything goes, right? And then you're in this like land of mystery, and then you can't do science. And I think it's the exact opposite. I think if you insist that the physical facts are the only facts and everything else are just these kinds of patterns that hold, that I think is the far more kind of Mysterian view. And I think it's perfectly fine to, and in fact, essential to have a research program where we try to understand what is the space from which physical structures are drawing these forms. So that's a long story about physicalism. And then I guess I'll just talk about the process philosophy. I think that's absolutely the way we need to start thinking about it. And there's a couple of papers that I wrote recently, really asking what does it mean to think of yourself, first of all, to think of yourself as a process, and to lean into the idea that every system, whether it be a learning organism or an evolutionary, a whole evolutionary lineage, you face the same problem, which is if you don't change, then you will either die or fail to learn. You'll disappear. But if you do change, well, then again, you're not the same thing you were. So again, you're kind of disappeared, right? So this idea, there's this paradox where if you think you're a persistent thing as opposed to a process, you face this paradox. But we can take that. So that insight has been around for a really long time. But we can take it further and use it to dissolve the sharp distinction between what James called thoughts and thinkers. In fact, he had said this, that thoughts are thinkers, and this idea that if we are a process, so here's the very simple argument: if we are a process and we are agential, then processes can be agential, and that raises the big question of, well, what other processes are agential, right? And so this is something that I've been working on recently, and then there's the one piece that I wrote starts with this kind of a really adapted story that I'm sure was a science fiction story that I read years ago, but I can't recall who or what. But it was this idea that these creatures come out of the center of the earth, right, and they're incredibly dense. So they come out onto the surface well, what do they see? Well, they don't see any of us, and they don't see any of our stuff, because to them, they are so dense. To them, all of this is like this really thin plasma, this thin gas that surrounds the planet. They don't see any of it. And so they're walking around, stomping all over everything, the way that we disturb patterns in odors of flowers and everything when we're walking through a garden. And one of them is a scientist, and he's been watching the gas, and he says to the others, I've been watching this gas, and there are these like patterns in this gas. There are these eddies, and they do things, and you can almost tell the agential stories about them. It almost looks like they have memory, and it almost looks like they want things. And the others say, well, that's crazy. We're real. We're physical beings. We're agents. Patterns can't be, patterns in the gas can't be agents. And by the way, how long do these hang around for? He said, well, they have a mean lifetime, about 100 years. And so, well, that's crazy. No, nothing interesting can happen on that scale. And so, right. So you kind of think, so you think about that, and you realize that the distinction between I am a real physical thing. I mean, we're not, right? We're obviously metabolic patterns that kind of hang around for a little while and change in various ways and come and go. And that really opens up this idea that, right, so if these kind of patterns, if our kind of patterns can be agential, and also it is very observer dependent what kind of patterns you're willing to take as possible agents, then what else are we missing, right? What other patterns all around us in various excitable media? And I could rattle off all kinds of weird forms of excitable media that have patterns in them. Wouldn't it be interesting to really have a research program where we take that perspective and we ask, okay, so who's in the kind of computational paradigm, what you're asking is who's the machine and who's the data, right? So typically you have this idea that this is this is the Turing machine paradigm, which I'm in no way saying this is sufficient for any of this, but it gives us an idea. So you have a machine, and then it processes passive data, and the machine does things to the data. But from the other perspective, you could say, no, actually, it's the data that's in charge. The data tells the machine what to do. And so could we have agential data? Could we have thoughts moving through a cognitive system that are themselves agents? The cognitive system is their environment. Maybe they're doing some niche construction and modifying their environment to persist longer. It's well known that certain kinds of obsessive, depressive thoughts and so on actually modify the brain. They actually modify synapses to make it easier to keep having those same thoughts, right? So you could do this kind of scale agnostic or scale free sort of thing where who's the machine and who's the data becomes very not obvious and very observer dependent. So that's I guess that's what I can say about that.
That was brilliant. We're over time on that question, so just answer if it's a yes, no. Do you get a sense that in the same way that quantum physics is challenging physicalism, your work outside of your sphere might be doing the same, or too early to tell?
Well, I mean, yes, I think that the interpretation. Okay, there's two ways to look at this. If you look backwards, so pretty much anything that we do, well, pretty much anything that anybody does, but certainly for our work, once we've done it, you can look backwards and you can come up with a physicalist explanation what happened. Working backwards, it's always possible. You can always zoom down to the lowest level and say, oh, well, that was just molecules moving around according to the laws of chemistry. There's no magic there. And that's true. It's never going to be fairies underneath. It's always, the laws of physics. But the real question is, okay, well, what's your next discovery then? Right? Then you have to ask, okay, so you have a worldview that every worldview facilitates and prevents you from doing certain things. So the question isn't, okay, let's have somebody do something interesting and then tell a physicalist story about it. The question is, what did your worldview allow you to do? And I definitely think that the things that we are doing and the things that our other people are doing in this space are suggesting that the physicalist view is limited. Thinking that these things are just emergent and we just got to kind of hang out till we find one is, I think that's very limiting. So in that sense, I think we're challenging it.
Beautiful. This next question was asked for me to read as well. Hello, Michael. As someone that struggles in math and would like to have more neuron energy directed to these areas of my math brain, does your work on bioelectrical communication disruption relate to acquired savant syndrome? And what tools could be used to channel neurological energy to areas of the brain on demand?
Oof, boy, that's hard. I don't have any specific details about that. I don't have a protocol that will, induce savant abilities or anything like that. I wish, but I don't. But what I can say is that if there are certainly plenty of clinical cases. In fact, Karina Kaufman and I, she's a student of mine, and she and I just wrote a preprint that covers a bunch of these cases, like acquired savant syndrome, like the rare cases of humans with massive hydrocephaly where they're missing a huge majority of their brain, but they have normal IQs and things like this. What this is all telling us is that we really don't understand the mapping of the hardware to the software. No surprise, because as I was emphasizing earlier, I don't think I don't think the physical structures create what we're interested in. I don't think you create minds or anything like that. I think you embody them the way that physical triangles embody the laws of geometry and so on. So because that and the mapping between these pointers and the thing that you get in the end is very indirect. We don't understand it at all. We clearly, for example, can't do the thing where, like in computer science, if you tell me how many transistors are on this chip, I can tell you how many bits of information that thing can hold. Right? That's we know what the mapping is between the cognitive capabilities of the system and the physical hardware that you have. In neuroscience and in cellular biology in general, we don't know that. We don't know how much tissue does it take to do specific things. So if somebody's held up so if you didn't already know what a human was and somebody held up a brain, and showed you and said, hey, how many people do you think are in here? You have no idea. We have and in fact, we still don't know because of dissociative identity disorder. You have a number of personalities in there. You can have cases where the mass is extremely small and you have normal IQ. You can have multiple personalities jammed into the same hardware. You can do all these things, and so I think we don't really understand the mapping, which means that it may well be possible to get very significant gains in, let's say, in intelligence, in other things that we're interested in, by fairly small tweaks of the structure. I don't know. IIT, yeah, that's interesting, right? Yeah, I don't know. It's unclear. So Fawn just asked what the implications are for IIT. I mean, it's unclear. To me anyway, how integrated information maps onto intelligence, for example. It's clearly measuring something important. But I think it may well be possible to have massive improvements. I think we just don't understand what the hardware is capable of at all. And I think what I say in that paper, I mean, I don't really call out physicalism in that paper, but what I do say is, wouldn't it be nice if we had a formalism that could predict some of these effects? Not try to sort of explain them after the fact as some kind of error, kind of epicycles, right? When people were trying to explain the motion of the planets and they were trying to fix up the kind of this idea that the Earth was at the center, and they were trying to fix things up with putting these crazy epicycles on everything. That's how we tend to handle this in our traditional neuroscience paradigm. These bizarre cases, we sort of try to come up with some way that it's not really anything. And I think, wouldn't it be nice instead if we had a principal theory that said, 2% of the time you actually can have normal IQ with less than a third of the brain of a chimpanzee, which has been seen. And we don't have anything like that. We don't have any theory that actually predicts that should be possible. So again, it's a difference between looking backwards and trying to kind of paper over what you saw versus being proactive and being able to predict ahead of time that, hey, we should see this range. So yeah, so I don't know how to do it, of course, but I do think it should be possible.
All right. Can you hear me okay?
Yeah, I can.
Perfect. Hi, Michael.
Yep.
Such a pleasure to be able to absorb your wisdom and knowledge again here in the Amir's space and the Adventures of Awareness space. Yeah, all of your interviews and classes last year with Bernardo were just extraordinary. So this is exciting to have you back. So my question or my curiosity is around the themes of discovery versus invention, and as you said earlier, the space in which physical structures are drawing. So my question is, in your experiments that have yielded spontaneous and novel yet highly organized emergent morphologies, have you explored or encountered indications of retro-causality or temporal non-locality as the informational influence at play in what you've alluded to as akin to the platonic forms or the third angle or the richness of patterns? Does that make sense?
Yeah. It does. It does. Yeah, I was
Okay.
thinking about this. I saw this yesterday. I was thinking about it quite a long time. Okay, I don't have anything that I can point to that say, look, I have an experiment that shows retro-causality. Okay, so I don't have anything like that. What I will say is that we do have this interesting question about what is the temporal nature of these patterns. Right? If they're not coming from the physical, they're ingressing into the physical world, so there's some kind of connection, but we don't have any reason to think that that time applies the same way that it applies here. And so what does that mean? How might it work? So I don't know. This is like way on the edge of the things, all the things I'm saying now are kind of way on the edge of anything I feel certain about, right? So I'm just, giving some thoughts here. It may all turn out to be untrue. But here's my thought. One way to think about that space, and it's the way it's sometimes presented as eternal and unchanging. So these patterns just kind of they exist and that's it. And there is no time there. And so from that perspective, we can ask, is that retro-causality when they sort of act on things that happen? I don't know. But one way to think about it is that they're eternal, unchanging. My gut feeling now, and it's not like I have a fully worked out theory of this yet, but I'm certainly going to work on this, is that I don't think they're eternal and unchanging. I actually think that some of them, anyway, have their own dynamic to them. There's a chemistry, quote unquote, of what they're doing I don't want to even say before, but outside of ingressions into the physical space. And I'll give you a simple example of what I'm talking about. And this is based on some things that we're doing related to the work of this philosopher Patrick Grimm, who worked in the 90s and published some really interesting stuff. So let's just think for a minute about the different kinds of logical statements you can make. So you could say something like, pi is greater than 3. And that is a statement that has a single truth value and it's stable and that's it. So in that Platonic space of forms, if there was a region of it that was for logic statements, that thing would be like a rock. It would be like our equivalent of a rock. It just sits there. It doesn't do anything. It's true and it's always true. And that's the end of that. Now, what Grimm did was something interesting. He constructed another sentence that's the classic liar paradox, which is this sentence is false. Okay, and if you try to nail down a constant truth value for it, you can't. That's the paradox, right? Because it flips back. But what Patrick said, he did two things. One is he said, well, let's not try to nail it down. Let's give it a time axis. So if you give it a time axis and you just track its behavior, then what you see is an oscillator. It goes true, false, true, false, true, false, true, false. So now you have an oscillator, and then there is no paradox, right? If you allow it to have time, then there's no paradox. So imagine then a sentence like that in Platonic space. It's like a little buzzer. It just sits there and it vibrates. True, false, right? It has a simple dynamic, not super clever, but not passive either, right? You can visualize it doing that. Now, the other thing that Patrick Grimm did is to apply fuzzy logic to say that we can make sentences that are not binary. So we can make sentences that say, okay, let's see. So here are two sentences. Sentence X. I am 70% as true as sentence Y is false, and sentence Y will be, I am the negation of sentence X or something. I'm making all this up, but these are the examples he used. And so now what you have is a pair of self-referential sentences that have a dynamic to them. And then he went and plotted them. So now you have two axes, you have X and Y, and you can sort of plot them and do all these interesting things. So if you do that, you find out that actually those two sentences together have, if you want to flatten it, they have a shape. They make a structure. Some of these structures are fractal, by the way. Some of them are very beautiful. It's really interesting. It's really interesting stuff. And I'll if Amir wants, I'll put some links into the notes for later so you guys can see this stuff. And then, or you can let them have the time dimension, and then instead you have a dynamic thing that sort of goes around and does various things. Some of them settle. So, right, because what you're looking at is this is basic deterministic chaos theory. You're just, they're either going to settle to an attractor or they're going to, circle each other. Some of them are chaotic, so they make these crazy fractal things. But now they have more complex dynamics. So you've got your rock, you've got your buzzer, and you've got your some kind of weird dynamical thing that does something. It's sort of turning itself over in some weird way. So you could possibly go one step further, and we're still studying this. And I have a student working on this. The following, you can do the following. We've shown that if you have models of gene regulatory networks, which are really just differential equations by which one gene turns other genes on and off, you can show that by stimulating those certain nodes and looking at the output of other nodes, you can show learning. You can, for example, Pavlovian conditioning. You can associate two stimuli, one which triggered the response, one which never did. You present them together, and eventually the neutral one starts to trigger. It's like a Pavlov's the bell and the meat story. So you can train them. So now something very interesting happens. If we can train small collections of self-referential equations, could you train logical sentences? I mean, I know this sounds completely crazy, but there it is. If you have logical statements that together implement, in Grimm's kind of formalism, they implement this dynamical system. If you give it stimuli, for example, it's going about its merry way, and I want to stimulate sentence X, which means I just bump up the truth value by like 0.2 or something, right, temporarily, and then I take my hands off it. Like, you do that enough, do we see habituation, sensitization, associative learning, anticipation? I don't know, all the things that we look at in all of our systems. So now, you can sort of start thinking about the very weird things can in fact be not passive and maybe more than active in terms of information processing, and how far does it go? So you might be able to say that the space of patterns has very low agency patterns like geometric figures and things like this, but maybe there are higher order things, in Dennett's words, kinds of minds. Like who knows how complex these patterns can get, right? And that's then I don't know what to. I mean, all of this is just to say I have no idea what to say about time in that case, right? Because if you do have rich patterns in that space, what can we say about its time stream? I don't even know how to begin to think about that yet. But I think we're just at the beginning of thinking about those kinds of things.
Beautiful. Thank you so much. Okay, Alistair, did you want me to read that question? If you don't unmute, yeah.
I'm happy to say it then, yeah.
Great.
Michael, I apologize that this could be a very naive question. I'm curious what your thoughts are on the role of belief in placebo. Why is it that you have to believe it? And what's going on there? What's the difference between believing something and just wanting it?
Yeah, it very interesting. I recommend the work of Fabrizio Benedetti if you haven't already seen it. It's really amazing. It's incredible. And he does these brain scans and biochemical assays on people who think they've gotten a particular medication. They haven't, but they think they have. And his the kind of outcome from all of this, he says, this great quote. He says, "Words and drugs have the same mechanisms of action." And it's really interesting. Now, to my understanding, okay, now I'm not an expert on placebo effects. To my understanding, you actually don't have to believe it. And what we have in this thing I was talking about a minute ago about us doing associative conditioning to a gene regulatory network is a kind of molecular placebo, because what happens is, just imagine you have so here's this network. You find one node that it's going to be your unconditioned stimulus, meaning that when you trigger it, it fires the response. That's the meat. In the Pavlov example, you show the dog the meat, it salivates. You don't have to teach it to do that; it already does it. So that's called the unconditioned stimulus. Then there's another node. You tweak that node, nothing happens to the response. That's the bell in Pavlov's case. You ring the bell, dog doesn't care. No salivation. If you present these things together sufficiently, that certain networks will learn to associate that previously neutral stimulus into what's called a conditioned stimulus, meaning that eventually you just do that and the response will fire. Now, if you think about it, that's a really primitive form of a placebo, because what you've done is you've now convinced this network that you actually showed it the unconditioned stimulus when you really haven't, right? And so I think this is exactly what happens in these cases of when the patients, basically when a doctor of a certain age wearing a lab coat gives you an injection that's really great, and a much younger doctor, no lab coat, a pill instead of an injection, you get something but not really the same effect. All of these things are basically because we are an information processing system from the top down. And these kind of placebo effects happen extremely early on, that basically even something as dumb as a molecular network, 7 or 8 nodes turning each other on and off, it already has the chops to gain a new belief that guides the way that it reacts to stimuli in the future. I mean, that's learning and memory, right? So the only other thing I can say about that is that if I were to tell you that, with the power of my thinking alone, I can physically depolarize 30% of my body cells, right? Now, you would think that I'm either crazy or I'm talking about some bizarre yoga thing. I've got some sort of like mind-body medicine thing that I've been working on. Actually, we all do this. It's called voluntary motion. So in the morning, when you wake up, you have all these like long range executive goals. You're gonna, go to your lab or whatever, change the world, whatever your goals are. In order for you to physically get up out of bed and go do that, those very high level conceptual cognitive states have to be transduced through your body and make potassium and calcium ions dance across the membrane of your muscle cells. This idea of thoughts and goals directly controlling the material, the chemistry of your muscles, is something that we do every day, all day. And I think what's significant there is that how can we not have placebo effects when that's how the whole body works? The whole body is a transduction system to convert cognitive content into chemistry, right? And it's amazing. It's not it kind of is a magic superpower, but not the kind that that rare is rare or impossible, whatever. It's to have your thoughts actually move ions across cell membranes and activate glands and so on. So that happens all the time, and the fact that it happens at all suggests that there have to be placebo effects. Everything, almost you could actually say that almost everything is a placebo effect. The fact that you can get up out of bed and you think you can and you're going to is part of that whole information structure, right? Knowing how to control your body and so on.
Amazing. Beautiful.
Yeah, and I apologize if I've gone on and on, but I got about 4 minutes on this one.
Yeah, so if there's just 4 minutes left, I wonder if there's a question that you want to pick out that can be answered in 4 minutes, or if you remember any.
Let me see if I don't have the thing in front of me. Oh wait, I do. Okay, hold on. And I'm happy to if I've missed anybody, I'll do it in email. Just send me anybody who got missed, send me an email. Let's see. Yeah, the one on Federico Fagin's theory of quantum consciousness. I'm sorry, it's out of my expertise. I don't know. I did try to do some homework by asking Chris Fields about it, but he didn't really understand it either. And if he doesn't, that takes all the pressure off of me. I'm not surprised. I don't get it. Let's see. Yeah, how we go about selecting gap junction modulators, drop me an email and I'll send you. There's only a few chemical ones, so I'll tell you what that is. Emergent property. Consciousness is an emergent property of living systems. I don't know. I don't have a full-blown new theory of consciousness to offer. I'm working on it, but I don't have a new one to give you. But I don't think that consciousness is emergent from physical bodies. I think, much like I said before, I think that physical bodies are pointers that allow ingression of certain patterns, including what we talk about as consciousness. So I don't think we make minds. I don't either in development or in bioengineering. I don't or in AI or whatever. I don't think we make minds. I think we facilitate certain patterns, and some of those patterns are sufficiently complex and cognitive that we relate to them as minds. Let's see what else. Oh, scaling. Okay. When considering the scaling down of cognition, no problem that cognition doesn't bottom out going down. What happens if it scales up? And Rupert Sheldrake's notion that the sun and the stars are conscious. My point about that is as follows. Is it possible? Absolutely possible. But I don't think we can rule either way sitting in from the philosophical armchair. I think we have to do experiments. So if you want to say that the weather patterns are cognitive, do the experiment. Can we train them? Can we have some kind of meaningful interaction described by the tools of behavior science? And the same thing with the stars and the sun and everything else. Completely possible. I don't see why it wouldn't be the case, but I don't think we can say either way. I think it's just as wrong to say that yes they are as it is to say no they're not, until we've done experiments that show what kind of interaction can you have with them that you can have with conscious beings, or cognitive beings, let's say that. We know what kind of interactions you can have with cognitive beings, right? That's the whole spectrum of persuadability. With the simple ones, you can change their goals, you can train them, you can do different things all the way across, through communication and psychoanalysis and love and friendship and whatnot. So let's see it. I call all of these claims, these cognitive claims, I think they're fundamentally interaction protocol claims. So if you tell me that a system has X degree of cognition, what you're really telling me is that you think you can have this level of relationship with it using some sort of tools, right? It could be the tools of control theory, cybernetics, behaviorism, psychoanalysis, whatever. There's a bunch of tools. So yeah, if you want to make the claim that the ecosystem, the solar system, the universe, it has those properties, fabulous. Pick some of these tools, have that interaction, and show how it works, and I'm on board.
Brilliant. So we're at time, Michael. Thank you so much. Just amazing to hear your answers to all these questions. I know you have to go.
Thank you so much.
Thank you,
Yeah,
everyone.
I really appreciate it. Yeah, thank you all for supporting American Humane, and thank you for these amazing questions. Yeah, thank you also.
We'll send out an email with your notes and how to get in touch if
Cool.
it's okay. Yeah. Great.
Okay. Thanks everyone. Have a good night.
Have a great day.